I'm putting my audio on. That's fine. Can you hear now? I think it should be fine. Can you hear now? Sorry. Oh, great. Thank you. Sorry. So we are talking about Kepler data, and well, like I said, Kepler basically works on the. We don't have time to talk about it, but the earliest exoplanet detection, that's the one for which the Nobel was given, was basically radial velocity measurements. Okay, if you have a planet going around a sun, you will have in spectroscopy, you will see a shift in wavelength, right? And that is the radial velocity measurement. But that happens with spectroscopy. But Kepler and TESS both work on the principle of transits. So you look for this dip, and based on the dip, you actually detect the planet. So typically what is done with Kepler data is that if the planet comes in the front, we should catch at least 3 dips, minimum of 3 dips for a detection, something like a 3 sigma detection. So you should get 3 nice clear dips. Often the dip could be say 1% or whatever it is. Typically you want 3 transits. But the thing is, like here what I'm showing you is an exoplanet called HAT P7b. In this case you can see you have only one planet going around the star, and hence it's nice. But in real life, if you sit and analyze Kepler data, like our sun, you will have a multi-planet system. And all these planets will have their own time periods, right? So when I get these dips, it's an overlap of say 4 or 5 or 8, 10 time periods. So catching the transit signal is more tricky. But today we are going to deal with a single planet case, which is the simplest. There are ways of handling the other ones. We'll talk about that later. So in short, and the same data, in principle, Kepler data, is also useful for binary stars, because it's just looking at a certain patch of sky. It's about 1 million stars. So for all million stars, it's giving you light curves. Okay, light curves means the variation in the brightness. So if the star was also a binary star, also you will get this variation, right? So typically, a good chunk of this analysis can also be done if you want to work on binary stars in that same region. Okay, it will give you similar analysis. You'll see all the formulae we will apply essentially will also work for binary stars. So you can also use it for binary stars. These are typically for eclipsing binaries, right? So what we are going to do is we are going to use Kepler data to find the orbital distance of this planet. We'll find the radius of the planet, we'll find the mass of the planet, the temperature of the planet, and also the chemical composition. Okay, I'll show you how we do that, and let's see. So first I'll run you through this, and then we will actually do it. Okay, so we are going to go to this website. I will share that with you all. This is this website. Sorry, so let me go. I will share this one on Zoom as well as on this. This is the website from which we actually get the Kepler data, okay? And this is hosted by the Space Telescope Science Institute. And one minute. So this is the website from which we get the data. If we go onto this website, you will see that, okay, this is still stuck there only. So we'll go back there. Okay. So we'll do slideshow from current slide. Okay. So here, this is the website which is hosted by the Space Telescope Science Institute. This is where you get data for Hubble Space Telescope, James Webb, Kepler, TESS, all space missions of NASA. Okay. They are all available in this. And you can see if you go to this website, we can go there also and you can see it. You'll see data for various Kepler sources. Now, Kepler sources are named Kepler 1, 2, 3, 4, etc. A is reserved for the star, okay? So Kepler 1a, for example, is the star. And then the exoplanets are named as B, C, D, E, etc. Okay? So that's how the nomenclature happens. So for example, over here you can see this is Kepler 6b, okay? So 6a is the star and B is the planet. So you start off like that. And here if you see on this website, you get the time series data. Time series data is giving you the variation in brightness. And the other one is the radial velocity data, okay? So these are the two things which you will get from this website. We will do it, but I'll just first skim through this. And we are opening this in, we will open in TopCat. So typically what you will get is you will get data which looks like this. What is this? This is the brightness. The brightness has been normalized, okay? So normal brightness of the star is 1. Okay, it's scaled. And these over here, what you see down, these are Julian dates, okay? Don't worry too much about what a Julian date is. It's just a way of counting days in astronomy. Finally, you need the difference between them. So you don't need to worry about what are these things. But this is in short time, and this one is in short the brightness. But it is scaled to 1. Now you can see that you have various observations which are ranging from 1 till 0.99, which is basically to tell you the accuracy with which we are going to do observations, because your fall is 0.99, right? So obviously people do exoplanet studies on ground-based telescopes. But if you have a variation like this coming through atmosphere, it can also come. But then you won't get three perfect transits. So you remember we already put a 3 sigma kind of condition that you should get three nice transits. Because if it is an atmospheric effect, you won't be able to get that. So it kind of protects you. So on ground-based, people also do this. Instead, with small telescopes, even with 40 centimeter telescopes, people do this kind of light curve analysis. Like I said, with the restriction that you see that you get the transits often enough. Okay, now what do we do in this is an interesting thing. That's the only thing which we use TopCat for, is something called folding. Okay, see, this is the data we have. These are various points with various brightnesses. Okay, but how do I now get my data from this? What we instead do is we fold the function. Because you see, we have observations at different times. We have observations here, at different points of the light curve, right? But I want one nice light curve where I have all the points, okay? So what I do is I fold it. I fold this with the time period, okay? We do something called folding. And to fold it, the simplest function to use is the modulo function. I hope you remember what's modulo. For example, modulo 9 comma 4 is you divide 9 by 4, your remainder is 1. So your basically your modular is 1. So what you're doing is we are folding it. It doesn't make a difference how many time periods. We are only interested is how much after the crest or the trough, right? So we want to know the modular function. So this is the function which is also there in TopCat. You give the function which is y, which will be your column, which is the time column, and p is the period, okay? And what we do is you fold a function. So you see, this is the function. I have different data points. See, I have these data points here. Then over here, I have slightly different data points. But then when I fold it, you get something really nice, which is this. And this is what we use TopCat for. Okay, so we use TopCat to basically fold it. So that initial light curve which you saw like this, it gets folded to give me this. Okay, so this is one combined light curve which has everything, okay, in one light curve. So this is called folding. Yeah.
So now, if we want to find the period, we have to look at the light curve.
Yeah.
In order to fold the light curve, we also need the period.
Yes.
So how does that?
Yeah, thanks. That's a very good question. Thank you very much. So actually the period for Again, the audio. Acha, I've got to put the audio. Right. So I'm going to show you a fast notebook where you will actually see all these things being done. I would have liked to do it with TopCat, but we don't have the time now because we have a speaker who will log in now at 10. So I can't I have to give it to her.
Hello.
अच्छा ये नहीं आ रहा ना this thing. You can't see this thing. Stop share. Okay, that is coming as desktop to share. Maybe that's desktop. Okay. I'm sorry, I don't know why this problem happened. Okay, net is on. Net is on. Okay, great. So here you can see I have a collab notebook. I actually wanted to do it like Chetna did it yesterday, make you guys type and all that, but that won't happen. So there is, in AstroPi, there's a package called Light Curve, okay? So you pip install Light Curve and you will pip install Light Curve.
Priya, make me co-host again.
Okay.
Don't make me run.
Yeah, I'm making.
Can you minute bounce?
Yeah, done. Okay.
Because video is
What happened to the share? That time you could see the collab notebook? No? Oh, good. Okay, so let me do
And
share.
we can see.
Okay. What is that 1, 2 thing? Okay, so we go back to meeting. Okay, this is my screen. So I'll say share. This is share. Why is it showing me this nonsense? What is it doing? Why is it doing this nonsense? It's not mirroring. It decided to not mirror. Desktop. Gather windows. Okay, great. So here, this was the light curve thing which I was talking to you about. Right, so it's pip installed. Now these are Robel libraries which are there in Python which you need for this analysis. One is LightCurve, NumPy, Matplotlib, etc. Now, as part of the VO, you can get the Kepler. One, I showed you the website from which you can get Kepler data, or you can run it from here itself. You can actually search and get Kepler data directly from here, from Python. So you will say LK search light curve, Kepler 6, okay? So that will give you all the data for Kepler 6, okay? Now, once we get this data, which let it search, you will see that we have to clean the data. So you'll typically remove points at which we do not have data or you have outliers. Outliers can be because of any problems with the data, etc. So anything which has 5 sigma, more than 5 sigma, we throw it out, okay? So we do this, we remove and we normalize it. If you remember, we had everything normalized to 1. So we normalize it and we get it. So typically, if you see the light curve, this is the number of the points I have on it, which is 1 lakh, whatever, one see this thing. So this is my time and flux. If I were to plot it, you'll actually get the plot like this, which is a much denser plot, which is like this, which obviously, like you see it here, it doesn't make much sense. So now we have to do what we did, which was folding it. But we fold it, before we fold it, we need to find out the frequency. So we run this thing with this Lomskarkil method. You can read about it. It basically does Fourier transforms to find out the period. So if I actually do the period is this, I can actually, I can even insert a code cell and I can write, for example, period. So you'll see the period value. Sorry, this is not, okay. So what it's doing is it's making, this is the Lom's-Cargill periodogram. So this is the peak. You can see this is the peak at which this is the underlying frequency. So it plots this and it actually finds out the best frequency. Okay, that's why it had a problem. So you can see here, this is giving you to like, I don't know how many decimal places, more than 10. Okay, so I have an accurate this thing. Now I run this thing called phase fold, okay, in which I'm folding it by the phase. And once I phase fold it, you can now see my plot looks far better. Where is phase 2? Where did phase go? Phase. What is this phase 2? Okay. 1 minute, okay. Here it is phase 2. Yeah. So now you see you get a folded curve. So now in this folded curve, everything has come down over here. You can see it even more accurately, 1.1003, and your this thing is like 0.997. So you're doing it obviously much more accurately. You use this, concatenate it, and then there's a, here we've got more than one, you see for more than one. And we import math. And now what we do is, this is just a thing which is just added in to calculate those remaining quantities. So for example, I'll input the M sun for this thing is the mass of the star is 1.21 M star. M sun, sorry, M star is 1.21 M sun. The period value we've given, we already know the period value. And we obviously, one exercise you have to do in everything is convert it all to SI units. Again, which you can do with AstroPi. In AstroPi, if you remember yesterday what Sir showed you, you converted everything to whatever units you wanted. Safest is to just put in SI units. So you live with SI units and you will substitute for R star, T star, etc. and get all the values. So I don't know why again the net is gone or what. I don't know. It's taking so long to run this. So in short, you'll put all these values and you'll finally get your parameters. Yeah, I think I will wind up, I will share this with you all later on. So in short, when you run this all, you will get the parameters of your this thing and you can compare it with the values which we get for the star. So you can just Google also. If you just Google and you see Kepler 6b parameters. Okay, now a piece of good news. A piece of good news is this. So you're getting, these are all the parameters for Kepler 6b. So whatever you calculate, you can see how correct your values are. You can see typically exoplanets, the mass radius is all done in terms of mass radius of Jupiter. Okay, so the mass is so much of mass of Jupiter, the radius is this, orbital period, semi-major, this, that. You can see the temperature is 1500 Kelvin. Okay. The good news is that Kepler area covers more than 1 million stars, right? And we do not have 1 million astronomers to work on them, right? And therefore, a lot of a lot of Kepler data has been analyzed by people. It's a question of luck whether you find habitable ones. Suddenly, you see a news item, done by people where they discover a habitable planet and all that, because there are always. It shows in Russian all imports. Why? So in short, there's always a lot which is there in Kepler data, in the sense there's a potential for you finding things. Yeah, you can see, for example, there is this thing 1 month ago. Kepler is out since a long time, right? But you see this one, Kepler telescope finds Earth candidate 146 light years away, because there's still a lot of Kepler data which has not been explored by people, right? So if you get into analysis, maybe you can use machine learning. That's the standard way of doing it. And you run it for not one star, but you're running for 1 million stars, for example, or how many ever. And you analyze it, and you could probably, like in this case, you may find a cold Earth candidate, or you may find various. Often you see these things which come, TRAPPIST ones, or various sources, because people are still analyzing Kepler data. Kepler is an old story, but not all the data has been analyzed, right? So there's still lots of potential in analyzing Kepler data and getting values from that. So I'll end with this, because we have our next speaker, Shanshan, who's here. I'll just make her one
Hello,
minute. So I'll
can you
end
hear
with
me?
this. I'm sorry, whatever happened, happened. And Shanshan, are you ready? Why
Yeah, I'm ready. Can you hear me? Hello?
is this coming like this? Yeah, she's there, I think.
Oh, hello, can you hear me? Uh, I'm not sure if you can hear me or not.
We can't hear you.
Oh, okay.
Shanshan, are you there? Yeah, hi. Very good.
Yeah,
I've made you co-host so you can share your screen.
okay. Um, yeah, so this is my, okay. Hmm. Okay. Uh, hello? Yeah. So I will start. Hello, everyone. My name is Shanshan Li from National Astronomical Data Center from
Shanshan, just a
China.
minute. Okay, just a minute. We'll just adjust the audio. Yeah, just
Okay,
continue talking so that we adjust the audio.
okay.
Just give me 2 minutes. Yeah.
Mhm.
Yeah, you can speak now. Shanshan, you can start. Yeah.
Okay. Can you see my screen?
Yes.
Okay.
But you need to go on slideshow mode.
Uh, hello, everyone. Good
1 minute,
morning.
Shanshan. You need to go on slideshow mode. Yeah.
Uh, let me see.
You switch off your mic.
Oh. Wait. Okay. Uh, Hello, everyone. My name is Shanshan Li, and I'm from National Astronomical Data Center from China. And we also have a name called China VO. I believe on the first day you have all listened the Chenzhou Cui, Dr. Cui, to introduce what is IVOA, which is the International uh, uh, um, virtual virtual observatory islands. And yeah, China VO is part of this group. And this talk, I mainly focus on our China VO and what have we done so far with the AI. So this is my talk. These contents. First, I will briefly introduce the NADC, and then I will talk about our whole life cycle management of astronomical data, and then the NADC resources and services, and the last is the AI for astronomy. The first one, the NADC part. This part, I will start with the astronomical data because all the service and the resources is built on all this data. And yeah, maybe you have already seen this slide, but I want to go briefly about this. because first you can see we have already get into the era of exabyte very slowly because we are now building SKA, the CSST, the LST, all these big telescope and observatories. So we have to deal all this data-driven scientific all these data and to use this data to discover more science. So how can we manage all these data? So yeah, this is the book called Big Data. In this book, there is the slogan like astronomy, the origin of the information explosion. So this means that astronomical data is huge, and we have to deal all this with all these data. So these two slides you have seen the day before yesterday, which where Chenzhou Cui have already talked about all this IVOA stuff. So I will go briefly with this slide and get into the China VO. Our China VO is Chinese Virtual Observatory, is the national VO project in China, initiated in 2002 and by Chinese astronomical community, leading by national astronomical observatories, which I am currently working at. So under the guidance of the experts, including Dr. Jim Gray, Professor Alex Zastley, and Professor George Dolgovsky, China VO has been a very active member of IVOA and over 20 years. So for now, we have a platform, the China VO platform. We have unified access to online astronomical resource and services. We have all VO-ready projects and facilities, VO-based astronomical research activities, and all the public education services that will introduce later. So the National Astronomical Data Center is kind of the what we are building. We have been built for many years. So the China VO is more like the technical group name we are using, and we same people are building this National Astronomical Data Center. So we now use this name a lot. In China, the NADC was announced by Chinese government in 2019 as one of the first 20 national scientific data centers. So you can see we have built this for many years. And the key part of this data center is like we have a very complete and life cycle structure to support from the data source to provide online service and to allow computer, to allow astronomer, allow data analyzer, all access to our data and our service, and to do their research. So this is what I'm going to talk about, the whole life cycle management. So you can see to manage all the astronomical data is a very complicated thing, that from the observation proposal and to the observation to data process and to the end, the paper publication is a long chain. And I will talk about this through the project called LAMOST. Maybe some of you know that LAMOST is a spectroscopic survey. It was first the first phase of the LAMOST is from 2011, and every phase is like 5 years survey. And so for now, in its third phase. The total of in the first phase, the total of 9.02 million spectra were obtained, and including 8.17 million star spectra in all these galaxies and the quasar spectra we have already gathered. And so as the survey goes on, we have more and more data, and we provide more and more data release. So this is the like you can see bottom part of the screen. This is the building of the LAMOST, and in this the right side of this slide, you can see the mirror. The LAMOST has two mirrors, and all the spectra is collected by this fibers, and to get all the data in. So our data center is more like when the telescope get all this data, they transfer this data to our data center, and we responsible for all this data to release to the universal users to use all this data. So you can see if you click this link and to browse, so you can go to the LAMOST data release platform, which our center is responsible for, and the latest released version is the DR14, which may not have been published to international users, but only for the internal users. But if you go to the DR13, you can already use it, I think. So this is the as the LAMOST can have low resolution and medium resolution to part of the service. So when we provide user to browse online, we have to provide all a different way to browse all these data. So you can see this wide form is more like a Sloan search form that we learned from. We borrowed some design from their website, and to let user can search online by the coordinate, by the with more strings, by the format what they want. And we also can let user to select output format, like the CSV, JSON, whale table, all they want to use. So to make this usable, we provide output online tables like this. So if you just type in a coordinate, you can get all this information very quickly. So you type in the coordinate and the radius you want to use, and you can get all the spectrums which LAMOST observed. And so clearly you can have the feeds, PNG, and all this informations on the screen. So, and also you can download them. So you can download some spectrum you want to focus on, and select them and download the format you want. Or you can just browse them online. So we have interface, the visual data visualization platform. So you can see it here. You can see spectrum, what it looks like. If it's if you are familiar with the spectrum, you can quickly decide whether this is the spectrum you want. Okay, so for medium spectral viewer, as the LAMOST survey will point to one direction, and to get multiple medium spectral from one target several times during the same night. So usually the medium spectral contains many single spectrums. You can see here, and they have a combined spectrum, and you can analyze the single, and you can analyze them all together to see if there's they have some patterns and something you interested in. And also this is the download way I have already talked about, and so you can download. Of course, you can download as the link generate for you, or you can use the wget to have to download all the data. And of course, we have a VO services for Lamos data. Yeah, the three primary data access protocols are implemented, like cornstarch, the simple spectral access, and the TAP. For proprietary data, each interface embedded a personal token. So if you register online in our system, you will have your own token, and you can use your own token to get data. So to make sure not to share all your token with others. Okay. And also, this is a Tomcat way, and I believe all of you are familiar with. So if you use Tomcat, you can simply get Lamos data with this TAP, SSA, all these protocols. So very easily. So here you can see, you can browse the data in Tomcat. And yeah, we tried a lot to make Lamos data could be used worldwide. So that we tried to international collaborate with Sloan, with Visera, with the CDS, and with ESA Sky also to make Lamos data visualization on their platform, and also other groups. And here is result shows the related information at CDS. So if you go to CDS to search for the coordinate, you can see some Lamos data already related in, but the latest version will take some time to get on this system. And also we use the PyLamster package. This is the PyLamster is a Lamster data access package that can be directly invoked in Python. So we built this package. So if you are interested in this, you can just write down this link on the screen and try to see if you can put in use with this, and you can easily get feeds file using this platform, using this package, and to plot spectrum. So yeah, this is all the data, Lamos data. We have already worked on. All the works you can see here is the Sky, ESA Sky platform. So you can see the Lamos data, the spectrum inside the platform very clearly. And yeah, this all Lamos thing we have been done for over 10 years. As the time goes by, everybody knows that recent years the things develop very fast, and if you want to put it, make your data to used by more people and easy to used by people, you have to build more things like the API here. So we build the open API for Lamos also, and if you go to this link, you can get informations of this API and to use them easily. And thanks to all these works done by our team, the scientific outputs used to use the LAMOS data increased very fast in recent years. You can see as this data was this plot was drawn I believe in the middle of the last year. So you can see the 2012 data is not complete, incomplete. Yeah. So but you can see the trend, all the number of publications using LAMOS data and the citation count is all increasing very fast. So I just give an example with the LAMOS data, what we have done with this data. In the NADC, we have a lot services like LAMOS, like we built for the LAMOS. And we not only serve for LAMOS, we serve for many other projects, other telescopes, both in China, and we also mirror data from telescopes outside China, so Chinese astronomers can use them very easily. So here I kind of divided the NADC resources and services into two parts. The resources including the data storage, data access, the science platform, and also some worldwide tours and curriculum, which is the educational resources. So for the NADC service, well, is including data archiving, data managing, and some softwares we designed and developed, and also the services we humans put in, like to educate, to holding workshop, to training young astronomers, and to build the community and to do the education and public outreach. So here is the list of the NADC resources I have already talked about it earlier. You can see the data storage, data access, science platform, and HPC, and tutorials and curriculum. All these are our resources. And also, recent years we built AI-ready data resources so we can more connected with the latest LM trend, which I will talk about later. And so for the data resources, I will give a brief introduction so you can see how many data we have. The observational data size. We have over 1,000 data sites released. So the total volume is like 94.1 PB petabytes. It's huge because it's including FAST. All you know, you may know that FAST is a huge telescope. It generates a lot of data every day, every observing day. So this 94.1 petabytes data, maybe most of them are from LAMOS. And we also encompassing domestic observatory outputs, project submitted data, paper associated data, mirror data sites, and the popular science materials. So, and for the project and the paper related data sites, the data in so this is the a kind of a new thing which we developed in recent years. So we encourage our Chinese astronomers to upload their paper data to our center, so other astronomers can use easily. So you can see we have already collected all this over 200 paper data in our system. And for the NADC services, I just put on some examples like data archiving and management, and like workshop and training and education and public outreach. Every thing I list here is not a single title. It contains a lot of a lot of hard working and from the offline work and some online service to work together and to get things done. So I want to focus on one thing we built last year, I believe, and it is called Science Platform. And this is the platform a little similar you used with the Google Doc, and we built based on the cloud stack and Slurm. We set up the cloud computing environment tailored for the astronomical data processing. So in this environment, each user has a private space, which can be shared among different virtual machine and the desktop system. So in this platform, so we have already built upon some like Jupyter Live, like VS Code, like Kata, like DS9. All these softwares are used frankly by astronomers. So you can see also TopCat, all these softwares. So if you want to use all these things, you don't need to install them in your laptop, or you can easily register on our platform and apply for apply for a virtual machine and to use this software easily. And the one good thing is like we are data center. We not only have the software, we have data. So if you use the software on our platform, you can easily use the data in our system at the same time. So here is the channel view channels. I like a conclusion what I introduced before. Based on all these resources, all these services, we kind of build this front page, like this portal. So when the user come to our data center, they know where to go. If they want to learn more about the observation, they can click on the observation channel. If they want to use the cloud computing or science platform, they can use go to the channel. Yeah, you have to register. And this is you can see we even have a public channel. The public channel is kind of a specialized thing what we have done for many years, because we all we all interested to do the public education and outreach. So we have done the World Wide Telescope for many years, and we developed a concept called data-driven astronomy education and public outreach. And I believe from many years ago, we slightly built a platform called Channel V or Citizen Science Platform. Many of you may learned what citizen science is too. So like the Galaxy Zoo, so people can get to involve all the citizen science project, even they have no astronomy background, and to work with the astronomical data easily through all these projects. And this is the concept. So we can make use of the astronomical data much more wider than before with all this citizen science project. And the last part is the AI for astronomy, which is we currently working on a lot, and we think this is a big direction of our data center. So all of you know that the large language models is very is like the future, and everyone is working with this. It's the massive neural networks trained on vast text data to understand and generate human language. So from the 2017, when Transform was introduced by the Google engineers, and everyone is seeing that there may be a way for the for human to use natural language to talk with the computer, and this kind of come to true after 2022, the ChatGPT come out. So this ChatGPT is brought large language models to mass adoption and the productization. And so from that moment, scientists is always thinking that LLM are evolving from maybe not only a chatbot, it can be used for scientific research, and it can be a partner for our research, and especially for astronomers. Maybe we can do the AI for science using LLM from transition to see the patterns in data, to process data more faster, and to do our work more easily, and to write paper more easily, all these things. So it kind of make us think what an ABC can do in this trend, in this area, in this LLM area. So we kind of thinking that we cannot trust LLM very deeply, because it's generated kind of randomly. So we have to have a design to work with the LLM, to use it as it's good at, because it can talk to people, use natural language, so we can use this part. But we also want to maintain the part that the science should be done by the logical reasoning, and to use the algorithm, to use all this logical thinking. So so we can build a LLM and a domain model, and together to build a AI agent to make this work. Maybe this is our design. And all this design, this human AI collaborate scientific discovery system is built on the data resource I have been talking through all this talk. So this is the basic part. So we have to use all this data very well. And there's other other difficulties, like we cannot compete with the LLM the company, because they have massive capital. All the models are trained very expensive and very time consuming, and the scientists cannot do this. So so this makes us think how can we achieve it? Luckily, there is like a foundation model adaptation ways to use the fine tuning way to train train like domain model. So this means to start with existing open source models and adapt them to astronomy with minimal resources. Maybe this can work. So we kind of arrange all this data resources into AI ready way, so the LLM model can understand them much easier and trained much easier. And with a lot of help with different areas in different area scientists, we actually have a AI large model platform. And we have some domain models eventually. So here you can see we have 6 domain models. I think it's yeah, it's like a 4 model and 2 agent. Yeah, here. So some of them is for astronomy universal use, and some of them is focused on some domain like solar physics or time domain astronomy. So we have built this online. So all the people can use access this through this address. And but this is not enough, because this is only like model to talk with you using some area background informations. This is not enough for scientific research. And I wonder if you have already learned this concept called model context protocol. This is a protocol to standardize how AI models connected with external tools, data source, and services. So it's like a USB-C portal for AI application. So if you build a MCP for your services, like our service we have already provided for human for many years, so AI LLM model can understand all these services and use our services to generate contents, to generate their answers. So the directly think is like we build our MCP, use our Llama data services, and directly querying. So this MCP allow directly querying information and data through LLM, and it works. So later we build AI agent using all the MCP and all the data we have. You can see here is an example on the right side of this slide. This is an agent to analyze EPFXT observation data for the gravitational wave events. This EP is a Chinese telescope in the space. It's mainly for the time domain observation. So you can see this agent can help engineer a lot to fast understand and analyze EP signal, and it's already in use. And from all our works, we kind of during our works, we kind of understanding the AI, the data more and more, and we keep when we keep building all our services, we think we have to have a big picture of our service of our data center. So we kind of structured this called digital intelligent service. It has many years. It has many layers, but the core layer is called digital intelligent data services layer. it's API plus MCP. I have already introduced. So the API is kind of standardization, including the IVOA, AskQuery, OpenAI, all the things we have been working on for many years. And the MCP is kind of new thing, but it can be built very quickly using all our work before. And for the carrier layer, it's like a research platform designed for them, for user to use. It can have all the data, algorithms, compute, and models. And for the extension layer, so all the scientific application and all the scientific analysts can use this platform. So this is the what we are doing right now and what we are building in the future. And I hope we will have a complete structure very soon, and to make all the astronomers worldwide can use our platform and can work with our platform, use astronomical data very easily. So this is all the talks I want to give, and this is what we have done for many years. Hope you enjoy the talk, and hope you can give us some feedbacks about all this works. Thank you.
Thank you very much.
So I end my
Yeah, you can speak from here.
yeah.
So thanks so much. Thank you very much, Shanshan, for your lovely talk. And it's amazing to see the amount of work you all are doing. That's really very nice. Do we have any questions over here? Do we have any questions? Okay, I'll just check the chat. There was a question, I think, which Shenshoy already answered, which was about the website. Yeah, so I think it's fine. Yeah. So thank you so much. Thanks a lot, Shanshan. Thank you very much.
Thank you.
And I'm sure people will be very happy. At least I would be very happy to use all the services you all have. That's very nice.
You're welcome.
Yeah.
And I believe there is a hands up online.
Okay, great. 1 minute. I'll just read the question.
Yeah, can see probably.
Yeah. Yeah. Who is the one?
I'm not sure. Okay.
Yeah.
Yeah, the online.
Yeah.
Yeah, I think you can
Hello?
unmute. Hi.
Hello, am I audible?
Yes.
Of science.
Okay. Hello, Professor Shanshan. Thank you for the wonderful talk. I just wanted to ask if we have a data set downloaded from some other platform or some other telescope website. So on the China VO science platform, can we use the data set which we already have? Does it support that file, or do we have to re-download or re-access the data set from scratch on the platform, or does it support the uploaded files as well?
If you are seeing the scientific science platform, I was introduced. Yes, you can upload your own data, and only if it's not a very large data site. Yeah, you can use your own.
Yeah. Yeah. So thanks. I think, can you hear me? Yeah.
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 Yes, I saw it.
Yeah, thanks so much. Thank you. I don't
Thank you.
see any more question. Yeah. So thanks a lot, Chen. Thank you very much.
Thank
Bye-bye.
you. Bye bye.
Bye-bye. Right. So now, yeah, we'll have a coffee break now. Okay. And thank you very much. So please log in after half an. Yeah.